Screen recorder. Okay, start. So, in the last class we had started studying this new mathematical object that we are calling lattices, right? So, pictorially they are just points arranged in a grid, multidimensional or higher dimensional grid. So, in the input you are given basis elements, you are given vectors b1 to bm, and then the lattice generated by these vectors is integral combinations, right. So, the important thing here is that gamma i's that you are using, they are all integers. Why integers? Well, because in the problem of factoring polynomials, this alpha I and beta I that you used, they were integers, right. And moreover, this x to the I gk and p raised to 2 raised to k, these are polynomials, or these which will be seen as vectors with integral coordinates, right. So, everything here is happening over integers, and there you want a short vector. So, that is the SVP problem. SVP problem would be a stronger problem, stronger question. You want the shortest, you want a shortest vector in the lattice spanned by the vectors b1 to bm, but that is hard. So, instead what we will now do is we will find an approximate shortest vector, okay. And this algorithm, approximation algorithm, is due to L cube, Lenstra-Lowash from the 80s. So, this was a breakthrough result, and it is applied in many places, as we will see later. It started with the integral polynomial factoring. Okay, so the first pre-processing step, which is a good property to study for SVP, is that we can assume the generating vectors b1 to bm to be linearly independent over reals, okay. So, that will be kind of a simplification. So, why is that possible? So, let us consider coordinates of b1 to bm. So, consider their coordinates and the matrix B that they define. I use the same B. So, B1 has coordinates B11, B12 to B1 n, n is the ambient space. Then the same thing you do with B2, and finally with Bm. Okay, so this is the n cross m matrix of integers. Remember that m is right now m in this question may be less than n, equal to n, or greater than n. Okay, these were just given vectors, so m can be anything, but we will simplify it. So, the way we will do is you can think of it as a modification of column operations. Okay, so we will actually take combinations, linear combinations of the columns, and we will try to make this matrix triangular matrix. Okay, but remember that you are only allowed integral combinations. You cannot use non-integers. So, the first thing that we will do is we will take the GCD of B11, the first row. So, B11, B21, BM1. Okay, so let consider a combination of these BI1s. So, B11 to BM1, consider a combination which is equal to GCD of the first row. Okay. So, compute the GCD, and AIs can be computed by, for example, you can use Euclid's extended Euclid GCD algorithm. So, do that piece by piece. Okay, so simulate every step of the Euclid GCD algorithm on the columns. So, let us write that down. Apply the extended Euclid GCD algorithm, or let us say transformations, on the columns. On the columns of the matrix B. Okay. Fine. So, what do you get? You get a transform matrix so say the new columns are B1 prime to BM prime. So, for example, if B11 is smaller than B21, then what you will do is you will actually compute the quotient of B21 divided by B11, right, and that quotient you will multiply with B11 and then you will subtract it from B21. So, do that operation, and then you get a remainder and you get B11, then you divide B11 by the remainder and multiply by the quotient, take the difference. So, keep on doing this. Ultimately what you will have is GCD G in the top left corner. So, in this matrix B prime, 1, 1th entry becomes G. Okay, let us ensure this. Ensure that the top left corner becomes G after all these operations, and the remaining entries will become 0, right. So, let us look at this. So, the remaining entries in first row become 0. Right. So, which means that now the matrix B looks like, so B will be transformed to B prime, which looks like this. So, there is G and the remaining entries in the first row have vanished. In the first column you have some entries, they may be 0, they may not be 0, you do not know, and then you have this lower submatrix. right. So this is n cross m. So you get this n cross m matrix B prime. So what kind of this combined first step has achieved is it has made the first row in this normal form. So it's almost the zero row except the first entry being GCD. So what is this transformation? The transformation is B prime is basically B time B you did column operations, right? So it's a multiplication by a matrix on the right, B times U. Where U is what? So U follows Euclid's GCD algorithm. U follows each step of Euclid GCD algorithm. So what can you say about the determinant of U? Right, so that question is important, because you want to claim that the lattice generated by B and the lattice generated by B prime, they are the same. Okay, if they were not the same, then it will not be a reduction, right? Then looking at lattice B prime, we will not be able to get SVP of lattice of B. So now we want to show something special about U so that the lattices are the same. So the claim is that U is unimodular. What is unimodular? That the determinant is plus minus 1. That is, the determinant of U is plus or minus 1, which means that its inverse, so U inverse is integral. So once we show this, you can see that the lattices of B prime and B are the same, because the matrix you are applying, its inverse is also an integral matrix, right? So any combination that you take of the integral combination of vectors or columns of B, that corresponds to something in B prime and vice versa, right? Because you can multiply B prime with U inverse. So this will imply that the lattice generated by B prime is the same as the lattice generated by B. So what is the proof idea? Well, the proof is just that the division step, one step of Euclid GCD is division step. So AB is going to AB minus QA, which is equal to AB times 1 0 and 1 minus Q, right? And if you consider the determinant, so determinant of 1 0 minus Q1, this determinant is 1. Okay, so this is the only thing which is needed to prove that U is unimodular, because in one step of Euclid GCD you are doing division, you are transforming two numbers AB, so a vector AB to this by multiplying with a matrix which has a determinant 1. and when you repeat this, you are multiplying such matrices, so the determinant will remain 1 or minus 1. Okay, it may become minus 1 because you may be permuting the columns also. Okay, so when you permute column, then you may get a sign. So it will always remain plus minus 1 in the kind of transformations that we did. Okay, so that's it, right? That finishes the proof of, well, that finishes the first step. Now we have to focus on this blue part, the submatrix. So repeatedly apply so this trick is by Gauss and Euclid. So apply this trick to get a matrix B tilde so what is happening? Rho is becoming 0, right? If except in the first entry, the rho is 0. So you are getting a lower triangular matrix. Ultimately, you will stop at this. So sum A. So in the end, you will have only 0 entries, and the first few columns will be non-zero. Let's say m prime many. Okay, so we have 0 in the end, and the matrix A is a square matrix with which is actually lower triangular. Where A is lower triangular. And most importantly, the lattice remains unchanged. Okay, so we have a very nice structural property here. What we have shown is that given any input vectors with integral entries, we can reduce, without changing the lattice, we can reduce them to linearly independent. So A is lower triangular and invertible. Okay, so the rank of this remaining part is m prime. So whatever was the rank of the input vectors, that rank many vectors you will get. So first m prime columns, form a basis. Over reals. Note that m prime is at most m, and also since we are talking about rank now, it cannot exceed n. Okay, and it spans lattice that we already said. So this finishes the proof of the pre-processing step. So from now on what we will do is so we work with R linearly independent vectors B1 to Bm in the ambient space Z to the n, and we are interested in the lattice generated by them and we want a short vector. Okay, so now we will do some, we will actually revise some linear algebra. So given a basis of a vector space, of a real vector space, what you know is you can find another basis by linear transformations. You can find another basis which will be orthogonal, which means that the vectors, they will be perpendicular to each other. Okay, so the angle between the basis vectors in the orthogonal basis is 90 degrees. So how is that done? So let us revise the idea, basic idea of that. So in the vector space generated by this B, so B1 to Bm, okay, using coefficients from reals, there is an orthogonal basis. This is a critical, this is a very important property in real vector spaces, and the idea can be seen pictorially. So what you do is you have this vector B1 and you have some vector B2. So you project B2 on B1. Okay, you project this, basically look at the component of B2 parallel to B1 and subtract that component. So when you subtract that component, you will get this vector, which is the component of B2 orthogonal to B1. Okay, so pick this, call this B2 star, and let us call B1 B1 star. Right, so this is the starting point of Gram-Schmidt orthogonalization algorithm. Right, so you are given vectors, you start with the first two, you are given a basis, in fact, start with the first two, remove, project B2 on B1 and remove that component from B2. So what you are left with is called B2 star, and that is orthogonal to B1 star. Right, so the important thing here is this 90 degrees. Right, this orthogonality is what we want. So this two-dimensional idea is the most basic idea, and then we will build on this, we will make it higher dimensional. So let us make it symbolic first. So orthogonalize the vectors B1, B2 to B1 star is just B1, B2 star is B2, from that you remove, project B2 on B1 in that direction, right. So you have to take the unit vector. So it is this. So basically look at the direction B1 and project B2 on that, that is the component B2 comma B1 over norm of B1, and then in that direction you do the subtraction. So you can check that B1 star B2 star inner product is 0. Okay, this follows easily. And second thing is that the shorter of B1 star B2 star is the shortest vector in the lattice generated by the 2. Okay, so why is that? So this is an important point. This is basically a special case of lattices where the generating set or the basis is orthogonal. So in that case, SVP problem is very simple. You just look at the shortest basis vector. That will be the SVP. That will be the shortest vector in the lattice. In fact, the proof is just by looking at combination. So alpha 1 B1 star plus alpha 2 B2 star. If you look at the norm, again Euclidean norm. So this is just sum of squares. Okay, so now since so any vector in the lattice alpha 1 alpha 2 are integers, so alpha 1 alpha 2 are at least I mean either one of them is 0 or at least 1, right. So if alpha 1 for example is 1 or more, then this will contribute the length of B1 star square. So any combination's length will be at least the smallest vector. Okay, so this is an important thing to remember. Right, so this is the sum of square property, which is happening because of orthogonality, and this shows that lattices of orthogonal vectors, shortest vector is very easy to find. When you are given an arbitrary basis of a lattice, it may be impossible to, so there may not be an orthogonal basis, right? That's the issue. Lattice B may not have an orthogonal basis. So that is the hard case. So what do you do? So since we are only interested in approximation of the shortest vector, so we'll compute the Gram-Schmidt orthogonalization anyways, and then try to use it to estimate the shortest vector. Okay, so let us look at Gram-Schmidt in general, higher dimension. So we'll call it GSO. So this is just an extension of the picture we saw. So the first vector we'll call B1, B1 star, and then the other vectors we'll subtract the projections. So this is just a for loop. So Bi star is from Bi you subtract the components of the previous orthogonal vectors. So B1 to Bi minus 1 star. Okay. So B1 star to Bi minus 1 star is the space for which we have already computed an orthogonal basis. So you project Bi on that and just remove that projection. So obviously what remains will be orthogonal to the first I minus 1 vector space. So that gives you Bi star. This quantity will be very important, and so we'll call this quantity we'll give it a name. This is mu ij. Okay, so what combination are you taking of Bj star? So that is mu ij. Okay, so let us prove a, well, so it's an easy observation, you can prove it as a small exercise, that GSO gives an orthogonal basis. Okay, this you must have seen in basic linear algebra courses over reals. Is there any relationship of our shortest vector to Bi star? Okay, so for every non-zero vector in the lattice, let's call it B. B is at least Bi star. This is the claim. So this relates kind of the length of the vectors in the lattice to what you get after GSO. Okay, so if you just pick the minimum orthogonal vector in the orthogonal basis, you at least know that every non-zero vector in the lattice is lower bounded by this. So the shortest vector cannot be smaller than this. But we don't know how good an estimate this is. Okay, but let us start with this property. It has a simple proof. So consider this combination of BIs. since bi's we are assuming linearly independent, lambda i's will be unique and they are integers. For integral lambda i's, for lambda's integral and let us say lambda m is non-zero. Okay, something has to be non-zero because b is non-zero. So, let us say lambda m is non-zero. Let us now use the GSO basis. So, let us write b as lambda 1 b1 star, well, because b1 star is b1. What is b2 star? So, b2 star is, or well, what is b2? So, b2 is b2 star plus mu 21 b1 star. What is b3? So this pattern will continue, right? b3 will be b3 star plus this mu times b2 star times mu plus mu times b1 star and so on. So, in the end you will just get lambda m times bm star plus m projected on m minus 1. M projected on 1. Fine. Okay, and then you can look at the norm square. So, norms now, since you have written B as a combination of orthogonal vectors, you can use the sum of squares, right. So, you will get the coefficient of B1 star squared the last one, which is Bm star. So, what is the coefficient of Bm star square? Bm star square is lambda m square. Right. So, you get these sum of squares B1 star square, B2 star square, Bm star square with appropriate coefficients depending on the lambdas. And so, this is clearly because of the real squaring, this is at least lambda m square Bm star square. Okay, so which means that we have shown the norm of B is at least lambda m times Bm star, which is at least Bm star. So, we have shown that the length of B is at least as much as this Bm star, which contributes as a component to B, okay, which means that the min property is satisfied. So, this is at least the min of Bi star, right, which is what we wanted to show. So, this finishes the proof of the lemma that min of Bi star is a lower bound on the shortest vector of the lattice. So, what will L cube do? So, the L cube algorithm tries to make the angles in a basis of lattice close to 60 degrees. Okay. So instead of trying to achieve 90 degrees, which is what orthogonalization is, L-cube algorithm actually tries to get to 60 degrees. So you can call this pseudo orthogonalization. Okay, so it tries to pseudo orthogonalize the basis of the lattice because orthogonal basis may not exist, right? So you can only work with some approximation. And then in that basis, it will pick the first one. Okay, so just like we saw in the previous lemma that the smallest bi star may be a good vector to start with or a good length to start with. This is what L-cube algorithm will do. It will actually try to orthogonalize as much as possible around 60 degrees angle, and then in that basis, once it has found the basis, in that basis it will just pick the smallest one and output. Okay, this is roughly the idea which we will now implement. Okay. So let us define this basis now properly. So L cube finds a reduced basis of the lattice B1 to Bm. So these are lattice elements, say C1 to Cm. There will be m many because you started with m many, and number cannot change, and they will be integral. So remember that you want the same lattice, so they should all be in the lattice such that so the first condition is a bit mysterious, but you will see why it is important when we analyze. Okay, so this is the first condition. This says that essentially, so you first look at the GSO of C1 to Cm. So let us say it is C1 star to Cm star. Okay, let us just look at C1 star and C2 star. So what is this condition saying for that? So this condition is saying that this C2 star should be pretty close to what it would have been if you were able to implement GSO in the lattice. Okay, so if you were able to implement GSO, then this RHS, this Ci plus 1 star plus mu I plus 1 I Ci star, this would have been equal to Ci plus 1, right. So this is actually comparing the kind of the length of Ci plus 1 with C2 with C1, and it basically is, it is a way to in a way it is trying to ensure that C2 is not much smaller than C1. Okay, the ratio is kind of 3/4. C2 should be at least well, square root of 3 by 2 times C1. Okay, this is so it's a bit hard to motivate this. You will understand this only in the analysis. And the second condition it wants is that this after GSO on C1 to Cm, this so-called this thing which we are calling reduced basis, the mu ij should be at most half, where mu ij is defined as before in GSO. Okay, so the first condition is kind of saying that Ci plus 1 is not much smaller than Ci. Let's say that. And the second condition is saying, so mu ij, if you think of it as cos theta, right, this cos theta less than equal to half is, or cos theta around half would mean theta is around 60 degrees. So angles around 60 degrees. Okay, so this is what we define as a reduced basis. So in a lattice, can you find a basis where the vectors in this order, their GSO is the Ci plus 1 vector is not much smaller than Ci, so kind of increasing in length, and second is that the angle of Ci plus 1 on the previous subspace is around 60 degrees. So kind of orthogonal also. Okay, so kind of sorted and kind of orthogonal. These are the two ideas that we are trying to approximate here. Well, we of course don't know whether reduced basis exists, but our algorithm will construct it. So in particular, it will show that this exists as well and efficiently computable. Let us see the implications of this. So this in particular implies the condition 1, for example. Condition 1 implies that Ci star square is less than equal to 4 by 3 Ci plus 1 star plus this 4 by 3 mu square, right, and mu by second condition is less than equal to half in magnitude, so that is 1/3 then. Okay, which implies that Ci star is at most Ci plus 1 star, right, which is again saying the thing that I was saying before, that Ci plus 1 star is not much smaller than Ci star, and equivalently Ci star is not much bigger than Ci plus 1 star, right. So kind of order is being maintained by this, and the impact of this is when you repeatedly do this, what you get is that C1 star, what is C1 star? C1 star is less than equal to square root 2 times C2 star, then square root 2 square, right, and so on. So it will, as you increase I, you will get this ultimately. Okay, so C1 star is smaller than square root of 2 raised to m minus 1 times Ci star for all I. So now if you use this orthogonality of C1 star to, or you use the lemma that we had shown before, right, that in the lattice generated by C1 to Cm, so by the lemma before, we get that the shortest vector in the lattice generated by C1 to Cm will be at least, obviously, C1 star. C1 is equal to C1 star, right. So this is a lattice element. So the shortest vector is at least C1 star, since C1 star is equal to C1 is in the lattice. So the shortest vector is at least C1 star, and C1 star is less than equal to this thing 2 raised to m minus 1. Two raised to m minus 1 by 2 times the shortest vector. Okay, this follows from the above inequality. Because you know the orthogonal basis comparison of C1 star with other Ci stars. So using that, you can deduce that C1 star cannot exceed 2 raised to m minus 1 by 2 times the shortest vector, because it is unable to exceed that for any Ci star. Right. So this implies together, all in all, it implies that C1 is a good, C1 is in the lattice and it estimates the shortest vector well by this factor. Oh, maybe I did not define lambda L. Let me define that also. So lambda L is shortest length. In the lattice. So this means that C1 star estimates shortest length by a factor of 2 raised to m minus 1 by 2. Which is actually C1. Okay, so the first vector in the reduced basis is what you will output. Once you have a reduced basis, you will just output this. So that is the key takeaway out of the definition. Okay, so now we move to the final question, which is why does reduced basis exist, and if it exists, how will you find it? So we'll answer both these questions together and very constructively. So this is L-Cube's reduced basis algorithm. Okay, so the first step is compute GSO. Of the vectors given to you. So you will get B1 star to Bm star. This can be done efficiently. Next is you okay, let me first give the step, then I will explain it. So say I is equal to 2, so what you will do is you will calculate B2. You will change B2, transform it by see, the point is that, okay, what is the output of step 1? So this gives mu ij and bi stars, but mu ij's are real numbers, right? They may not be integers. So as a first attempt, what we will try is we will round off mu ij to an integer and just remove that component. Okay, so let's do that. So mu ij let us round it off. So round off to the nearest integer. Okay, so this is the transform bi. So we are trying to get to bi star, but we may not be able to do that. But we'll just subtract whatever nearest integer multiple of bj we can, which is this. So this will take care of the mu ij's being reduced to half or less, right? Remember condition 2, you wanted these projection let's say constants mu to be less than or equal to half. So this rounding off will make sure that it's less than or equal to half, but the first condition may still not be satisfied. So let us see whether it is satisfied or not. So suppose if there exists an I such that it's violated, okay, so LHS should have been less than or equal to this for condition 1, but suppose it is not, suppose it is violated. So if it is violated, what should you do? So the simple hack is you swap bi and bi plus 1. So you will swap them, but remember that GSO is very sensitive to order of B1 to Bm, in what order you are doing the computation. Now since you have swapped Bi with Bi plus 1, this will change the GSO calculation, so you have to go back to step 1. Okay, so go back to step 1. Again, you will try to approximate the Bi star in step 2, and after you have covered all the BIs, then you will move to step 3, where you will try to ensure condition 1. If it is violated, you will again swap, again go to step 1. Okay, so you will keep doing this, and when you will output the answer. Okay, so this is the reduced basis algorithm. At this point, it is not clear why it will work or whether it will ever stop. That is the first thing. If it stops, why is B1 to Bm a reduced basis? That is not clear. So we will do this next time.